Math 265A, Cuesta College. I'm Joe Vasta, and we are doing section 5.2, definite integrals. So we've already covered something called indefinite integrals. Now we're going to look at this new concept. And so what do I have here? I have a parabola, x squared minus 5. It's your standard parabola that gets shifted down 5. And we're investigating this time interval from 0 to 3, or, I call it a time interval. And we've had these things called Riemann sums. This is the left Riemann sum. This is the right Riemann sum. We also had the midpoint Riemann sum. And this notation looks very intimidating. But all you are doing is adding up the areas of rectangles that you put under the curve. Okay, and they have their base on the x-axis. Well, this one is going to be completely different. Okay, so I know this notation looks bad, and I put it there just to scare you. I mean, this is really height times base, and you're adding up lots of them. So let's see what we do. I'm not going to crank out the calculations, like I did in the last section. But I want to show you something that when you partition this up, so we'll just say, 3 rectangles. Okay, so it's the same graph really, and I'm putting 3 rectangles, partitioning up the, let me fix something here. The interval from 0 to 3 into 3 rectangles. Actually, I don't need to fix something. Left endpoints of the subintervals gives me these 3 rectangles. And now these 3 rectangles are below the x-axis. And when you do the Riemann formula where you have f of x sub I times delta x, your delta x is 1. But the function evaluated, like right here, using this point right here, because I've used that point, and this point, and this point, the function actually gives you negative values like -5, -4, and -1. You add those up, you multiply them by 1, the area then ends up being a -10. So in a pure sense, we really can't call that the area anymore, and we are going to actually call that an approximation of the net area. And we've heard about that when we did I think it was bug 11. Now if you use right endpoints, so I partition this up into 3, I have a dot right here. And you won't be doing this in 5.2. Dot right here. But this dot right here, that gives me the altitude of this blue rectangle. This dot right here gives me the altitude of this middle rectangle, which the altitude is negative, and same with this. So when you actually do this net area, there's actually 1, 2, 3, 4, 5 that are in the negative region below the x-axis, and 1, 2, 3, 4 which are in the positive region. -5 plus 4 is -1, and that's that's how we're getting these. These are just the areas of the 3 rectangles. Now probably the reason this is new is because the ones that we did in 5.1, we always gave you functions that were flying above the x-axis. So when the function flies below and above, the Riemann sums give you the net area. The net area is, you take the stuff that's above the x-axis, that's going to give you a positive part of the area, and you add it with the stuff below, and that's going to give you the negative part. Let's go ahead and do L6 and R6, and here's what the pictures look like. I'm not going to color them now because that would have taken a lot of time. And look at that. I mean, look at how they compare. We went from -10 to -8.1, and then we went from -1 to -3.6. And so these are a little more accurate. And so what we're trying to do is we're trying to get an approximation of the net area. Now the net area represents the displacement of an object if this was the velocity function. And notice I used the 6 rectangles, come from the 6 intervals, and you take the left side. So I've used those guys, those dots, as the heights. So this one actually has a positive one, but these rectangles have more area than the one right here. So that's why we're still negative. These ones right here are 6. I'm taking the right-hand side, and that's how I'm getting these heights. So those 2 rectangles will have a positive area, and these 4 rectangles here have a negative area. And then when you add them all up, you get negative 3.6. Okay, so I kept going. I went L12 and R12, and you can see, you know, this is actually went from negative 8 to negative 7. This one went from negative 3.6 to negative 4.8. And hopefully that's a clear image there. These will be included with the PDFs. And then I decided, hey, I'm going to go R24 and L24. And notice these, you know, this got a little bit more negative. You know, went from negative 4.8 to negative 5.4, and this went from negative 7 to negative 6.555. So that's L24. So then I decided to go really crazy and use 100 rectangles. 100 from the left and 100 from the right, and look what that did to my numbers. Went from negative 6.555 to negative 6.1, and then negative 5.4 to negative 5.865. And so this is using 100 rectangles. And then I'm going to use 1,000 rectangles. And when I use 1,000 rectangles, I end up getting negative 6.014 for the left. And when I use the right endpoints, I get negative 5.987. So, you know, I mean, we could have kept going, but if you had to guess what the net area was, that's this top part minus the area of the bottom part. It's going to be negative because there's more negative, you know, there's more area below the x-axis. You would probably guess these guys are kind of getting closer and closer. You might even say that they are converging, which is a new word, to some number. Maybe you can guess what that number is. And I actually made this one be one where you probably could guess. Okay, so we'll come to that. So if I were to keep throwing more and more rectangles onto that curve, I would actually get the exact area. So that's what it would look like. And let's just take the right Riemann sum, but you could have put Ln there, or even the midpoint Riemann sum. You take the limit as n goes to infinity. That means you are making the rectangles go to infinity of this Riemann sum, which does height times the base. Then this is going to be exactly the net area, which, if this was a velocity graph, would give you the displacement over the time interval from 0 to 3. This is the net area from 0 to 3. Let me go ahead and write that there. So this is 0 to 3. Displacement from 0 to 3. And now, so here is the new notation. The new notation is the definite integral. It's called the definite integral, and it looks like the indefinite integral. The only difference is you have little numbers there on that integral sign. Okay? And does this have something to do with antiderivatives? We're going to see this in the next section. We have to guess the answer. So what do you think our answer is? Well, when we saw this right here, hopefully you guessed that these guys are getting closer and closer to negative 6. So negative 6 really is the net area. It's the blue area minus the red area. And so you're actually at a deficit because there's more of the red than there is of the blue. And so that is what this is about. Now your book is going to define something called the general Riemann sums, where the lengths of the subintervals of the rectangles, or actually we've been calling them the bases, are not necessarily equal. And they say that a function is integrable on an interval if the limit as n goes to infinity of these guys right here exists and is unique for all general Riemann sums. So there's a lot of theory in the book, and I tend to I've already done a lot of stuff. I don't want to get too much into the theory, but just remember that this notation right here means net area from 0 to 3. And also gives us the displacement when this is a velocity. Okay, so let's go ahead and define some terms. We have, you've heard this before, the integrand. The integrand is really, so we're looking at this, it's just the f of x. So the integrand is f of x. Okay, then we have our variable of integration. The variable of integration happens to be what's right there, so there's an x there, and so x is our variable of integration. Now we could have changed this x and this x to like w's, and then you would have f of w dw, and then your variable of integration would be w. In the end, when this is all so in the next section we're going to learn how to compute this. When we're all done, that x is not going to be there and you'll have -6 for the answer. Okay, so here's something really new. We have the lower limit of integration. The lower limit of integration happens to be the lower one, so that is 0. And then we have our upper limit of integration. And the upper limit of integration is the 3 in this example. Notice how this mimics this right here. When we were adding up rectangles, we went height times base, and if n was 4, we did that 4 times. So you're adding up a finite number of rectangles here. And so you have summation, which is a sigma sign. Sigma is the Greek letter for s. Look at this. There is a stretched out s. And now what this means is you are making your rectangles go to infinity in terms of how many rectangles you have. Here's your function, f of x. And then here is delta x. Well, now it's dx. So you can see some similarities, and this right here is the limit of any general Riemann sum. So, and we have -6 for our answer. So in integral calculus, which we're kind of getting into, we have something where we will have a real-life problem, and to solve that real-life problem, we can slice a region into parts, kind of like what we did with rectangles, and then we sum the parts and take the limit. This is sometimes called the slice and sum method, and it's just something that you're going to see, especially in the next calculus class. So we have displacement. Okay, so this was something else I want to point out. We have displacement, which is that right there. How do I get total distance traveled by the bug? The total distance traveled by the bug would just be the total area. So we would not count this red as a negative area. We would say this is a positive area and that's a positive area. Well, how could we write a formula for the total distance traveled for this? Well, it just so happens that you can get the formula by taking the absolute value of this function and integrating. So I don't know if you remember, if you take the absolute value of a common function, what it does is it keeps everything that's above the x-axis, and anything that's below the x-axis, it gets reflected above. And so the absolute value of that graph would look like this graph right here. You see, so all the stuff that was below gets reflected above. And so, if you want to know the total distance traveled, and this is like a bug problem from 0 to 3, the total distance traveled would be the definite integral from 0 to 3, not of f of x, but of the absolute value f of x. And that is how you would find total distance traveled. Now, we don't know how to crank these out yet, and we think this definite integral has something to do with the antiderivative, and it does. This is just FYI, and we can come back to this. The total distance traveled is actually 20 root 5 over 3 minus 6, or I'll round it to 3 decimal places, 8.907. Okay, so now if we were actually doing a bug problem, we would say feet. Okay, and that's what happens when you add up that area with that area. Okay, and so that's what you get. Now, we're not going to really have to do that with parabolas in our homework in 5.2, but we will do that in future sections. Okay, so we want you to get used to this notation. And now let's go ahead and do some kinds of examples. And this is going to remind you of when we did bug 11. Another picture that looks like this. So look what we have here. We have a function f. It kind of goes up like this, down like that, and here's the x-axis. It goes up, goes like that. And so we're asked, so this is new notation for us, these definite integrals. There's two definite integrals here. Our first definite integral happens to be the integral from -2 to 7, f of x dx. And so what this is this is the net area. Which means, okay, so let me explain the graph. Those are points on the x-axis, -2, well, there's 0, and then 4 and 7. These guys right here, these numbers right there, happen to be the areas either above the curve or below the curve bounded by the x-axis. Since this one's above the x-axis, that one, you know, I'll circle that in blue, and same with the 3, so this one has area of 3 here. Below the x-axis, we have an area of 5. We are integrating from -2 all the way to 7. And so what is the net area? The net area is -1. Okay, and then sometimes we would call this the displacement from -2 to 7. You know, if f equaled the velocity. Okay, so now what we have here is the next problem. It says the integral from -2 to 7 of the absolute value of this graph. So the absolute value would take anything that was below and actually reflect it above. Now we don't have to draw the graph. All we have to do is add these 3 numbers and not have that be a negative area. So this is sometimes called the total area in that interval. Sometimes, and I think your book just calls it the area. Okay, so it's the area from -2 to 7. So there's a difference between net area and total area, and we are going to add that up. We end up getting 9. Now, what did this have to do with? This had to do with the total distance traveled when we did the bug examples from the time interval 2 seconds ago to 7 seconds. And this is if f equals the velocity. Okay, so now it's about time. In your book they have all these properties of definite integrals. I'm going to go show you the first 2 properties, and they have everything that you're going to look at these and go, oh yeah, we know that. So here's the first 2 properties. If I could get this, oh man. So here's the first 2 properties there. I don't know where to put them, I'll just put them right there. It says the definite integral from a to b, f of x dx, is the net area displacement in a to b. You're probably sick of me saying that again and again, but that's very important. And then this one, the definite integral from a to b, the absolute value of f of x dx, is the total area. If you're doing the bug problems, it's the total distance traveled in the interval a to b. So those are 2 properties you'll see in your book. We've been looking at those. Why don't we go ahead and do a few more problems that involve this graph right here. So if you try reading the book, you might get intimidated, because they like to put lots of the Riemann sum notation. But in terms of the homework, it's not going to be that bad. Let's go ahead and do this problem right here. Same function. We have, let me go ahead and circle those areas. Those are positive areas, and this is a negative area when you're doing net area. We are trying to find the integral from 4 to 7 of this function of f of x dx. Okay, so notice that when we're doing this, we're not doing Riemann sums anymore. These are limits of Riemann sums, but all we're doing is just figuring this out looking at the picture. So from 4 to 7, you have the net area of 3. Okay, so that one was just to practice a little. Now look at this one right here. This one says from 4 to 5. Now we don't have a point for 5. I'll put 5 right here. And then we go plus 5 to 7. Okay, so let's go ahead and do this right here. And take out the yellow. I can't even find stuff anymore. So this guy right here is this net area, which is all above the x-axis. And then this guy right here is this net area. Okay, so we don't really know, based on the picture, what the yellow is. We don't know what that yellow is. And we also don't know what the orange is. But we do know together, if you add the yellow part and the orange part, you get 3. And so that is the deal, that if you have something that goes from 4 to 5 and then from 5 to 7 of the same function, this actually equals, not that you have to write this down, we already know the answer, that this is the integral from 4 to 7, which is the one we just did, f of x dx, which is 3. Now, why would I do a problem like that? Because this is going to illustrate our next property. Oh, by the way, my properties are probably in different order than your book's properties. I put my properties in the order of my problems. And so here's the next property. It says the integral from a to c of a function plus the integral from c to b of that function is actually equal to the integral from a to b of that function. Okay, so it's almost like we're saying it's this area plus this area, and that's what we did. Let's go ahead and do problem number 5. Okay, so this is really weird what happens here. When we integrate, we actually slide along the x-axis. We're going from 4 to 7, and we took the net area, which was 3. Now, this one's saying slide backwards. So the integral from 7, and now we're kind of going backwards to 4. What that actually equals, since you're going backwards now, is that equals the opposite of what you went when you went forward. So this is going to give you -3. Now, it still might upset some of you that the bigger number is here and the smaller number is there, but this is legal. We're just defining this notation and seeing some properties of it. Some of these properties are definitions, and some of these are just properties of areas. And so this is property 4. Property 4 says you have the integral from a to b of a function. It equals negative integral from b to a of that function. Okay. Let's go ahead and do some more problems here. So problems 6 and 7. Now I went ahead and repeated the results of problem 3. The integral from 4 to 7 of this function is 3. Okay, so problem number 6. We're saying the integral from 4 to 7 of 2 times this function. Now, 2 times this function, graphically what that looks like is each y value that you see on the function, like you have a y value there, it's going to be twice the y value. Okay, so 2 times this function is going to be like a hill, at least this part, that's going to be like twice as high in all spots. Okay, so any guesses on what the area would be? That's kind of silly. I should have probably made it a little higher, but I'm coming off the paper. Any guesses on what that area would be if the area before we went 2 times it was 3? Well, the area is actually going to give us 6 when we go 2 there. In fact, there's a property that says if there is a constant there, you can pull that constant outside the integral sign. And so this is really just 2 times, and we already have that. That's 3, which is 6. This brings us to the next property. So these properties, here they are. So here's the property. It says you have a constant here. You know, I didn't say anywhere on here c is a constant, but you could pull that constant outside the integral sign. That's all it means. The integral of a constant times a function equals the constant times the integral of a function. Let's go ahead and do problem number 7. Now this one is really weird. Okay, I'm going to go ahead and put 5 here again. 5. Now where is this integral going from? It's going from 5 to 5. Wow, we sure went far. So going from 5 to 5, you have this region here. Here's the region. You know, before your region would look like below a hill or something, and now the region just looks like a line segment. What is the area of that line segment? Well, it doesn't have an area. So when you go from 5 to 5 on your integral, or you go from 7 to 7, your answer is going to be 0. I believe your book calls this one a definition, but probably don't want to quote me on that. I think if I remember right, that's what they called it. So here is another property. Property that says you have a definite integral and you're going from, whoa, okay, so my property is written incorrectly. I just typed this up really quickly. That's alright, I'll fix it. You're going from A to A. Okay, so you really haven't moved any, and you're trying to find the net area. It's 0. Okay, let's go ahead and do a few more problems that illustrate some properties. Oh, look, we added another character in this story. You know, this is F, this thing that goes up and down. And this guy is G. You know, you could say, oh, well, G has the equation that looks like this. That looks like y equals, and then there's 2. Y equals 2. Okay, we have the definite integral from 4 to 7 of this sum. Now, if you're thinking like in terms of pictures, how would you add two functions picture-wise? Well, you would add at each x value, you would add the y values. So what would happen is the sum of like this and this would be a point right here, and the sum of this and this would be a point up here. So it would be almost like when you added something with a horizontal line, it would almost be like this picture gets translated up there. Okay, so it looks like that. That's how, I'm pretty sure, yeah, because you would add that with that. I mean, it's not perfect. And so when you're adding this, it's almost like you're adding the net area of G from 4 to 7. And then if this is really the same as this, you're adding that to the net area of F from 4 to 7. So bottom line is, I may have talked too much on this one. You're adding two functions. It really is this, the integral from 4 to 7 of f of x dx plus the integral from 4 to 7 g of x dx. So that's really what it is. Now some of these properties are true because what we have is we have the definite integral, which happens to be something called, you know, the integration is actually something called a linear transformation. And some of you will find out about that when you hit linear algebra and differential equations. But if that was too much for you, let's go ahead and finish this. What is the net area from 4 to 7 of f? Well, it's 3. This one might be trickier for some people, but I don't think it's that tricky. The scaling on the y-axis might be different from the scaling on the x-axis. But look what you have here. The net area, this guy right here, is a rectangle. It's this rectangle right here. Okay. Well, do we know how to find the area of a rectangle? Yes. This has a base of 3 and it has a height of 2. So the area of that rectangle, I think, is 3 times 2, which is 6. So I have 3 plus 6. And this gives me a 9. So getting back to our properties here, this property number 7 says you are taking the integral of a sum, the definite integral of a sum. It's the sum of the definite integrals. That's all it says. And guess what? There's another one that says the definite integral of a difference is the difference of the definite integrals. And that's what we're going to do on our next example. So look at this right here. I mean, we can write out that step. You might not want to write out that step because you know what you're going to do. You're going to go 3 minus, and the definite integral of g is 6. We already talked about that. And this gives you -3 for your answer. And so we have just covered all 8 of those properties. And those 8 properties you can find in your book. There's actually 3 more properties, and it's not like it's not like you won't be able to do your homework without these 3 properties. Let me go ahead and just show them to you anyway. Here they are. You know, it might be best to just look at this here. It says if f of x is greater than or equal to 0 in some time interval or some interval, and let's just look at 4 to 7 because that's what we've been doing. So here is f of x, it's this hill here. Then So it's just saying if your graph is above the x-axis, it's saying that your net area is going to be greater than or equal to 0. That kind of makes sense. The graph is above the x-axis in a time interval completely for all those things in that time interval, then your net area is going to be greater than or equal to 0. There's another property that we didn't put, but it's kind of the same. If your graph is below or touching the x-axis in a time interval, then your net area is going to be less than or equal to 0. So that's not written on there. And it's not like you can't do your homework without, it's not like you can't do your homework not knowing these. These are just some things about definite intervals. Here's another one. It says if f is less than or equal to g, which we actually have here for the whole graph, for a to b, then it says the net area of f on that time interval is less than or equal to the net area of g. And that kind of makes sense. I mean, g is above f, maybe sometimes touching it. It's just saying that g is going to have a greater net area. Here's the last one that will help us prove fundamental theorem of calculus. You've got these two numbers, m and m. Here's the small one, m, little m, and the big one, big M. And if your function is between those two numbers all the time in this time interval or in this x interval, then m, b minus a, less than or equal to the net area, less than or equal to m, b minus a. So what is this? I mean, you kind of already have one here. This is your m value. This function is, our function f is below the m value of 2. Then we can actually have one below. Maybe this says y equals -5. It's just saying that the net area is in between this. Now b minus a is the base of the rectangle, and m is the height of that orange rectangle. And so if you have another horizontal line that is below this graph, it's just saying that the net area of your original function will be in between those two rectangles in terms of net area. Anyway, so let's go ahead and move on and do a few other problems. We've pretty much covered everything in this section. There's a lot of stuff here, by the way. So let's go ahead and do new problems. We'll start the numbering again. And this will be for new problem 1 and 2, where we're finding these definite intervals. So they'll ask you to do something like this in your homework. They'll say, oh, well, and there won't always be piecewise defined functions, but this one is. So here's a piecewise defined function. And we are going to graph it first, because the only way we can compute these right now is by looking at pictures and doing things geometrically. So your book's going to say, use geometry to do this. What they mean is do it like I'm going to do it here. So let's go ahead and draw an x and y, the x and y axes. So we'll go like this, and maybe it's better on grid paper, but I don't have the grid paper with me now. I think the hardest one to graph will be the first one. So let's do that in a different color. I'll use purple. So it says y equals this. So y equals the square root of 4 minus x squared. I'm going to square both sides of that equation, and I'm going to get y squared equals 4 minus x squared. I'm going to bring the x squared to the left-hand side. X squared plus y squared equals 4. That is a circle. So is this top one a circle? No, this one's a half circle. And what happened is, when you squared both sides, it gave you the full circle. This happens to be the top half of the circle. So if you were to go backwards and go from here to here, you would do the square root property. This would give you plus or minus the square root of 4 minus x squared. The minus would be the bottom half. So we have the top half of a circle that has radius. So now we're thinking back to maybe things we haven't done for a while. Radius is 2, centered at 0, 0. And I'm going to draw the top half of a circle, but I'm going to do it from -2 to 0. So it's really just going to be not the top half of a circle, but a quarter of a circle. So here's 1, 2, 1, 2, and I'm going to go like this. Now, why did I stop there and not go all the way down? Because of this right here. This guy lives from -2 to 0, and those are x values. Okay, the other ones are not as dramatic. This one right here is y equals 2 minus x, and that lives between 0 and 3. So I could just plug points in there, like if x is 0, y is 2. If x is 1, y is 1. If x is 2, y is 0, and then I'll put x equals 3 in. If x equals 3, y is -1. Okay, so hopefully those guys all lie on the same line. It's not perfect with grids, it would have been better, but oh well. And then I have an open circle on top of a closed circle, which then it's a closed circle, and then this guy right here is an open circle. And then this guy right here is even easier. You know, what is he? He's y equals -1. Y equals -1. And he lives from 3 to infinity. So I guess I'm going to be putting a closed circle on top of that open circle and drawing it like this. Okay. So there's my graph of f. And we are asked to find the definite integral from -2 to 8. And I don't even know if I can make 8. Let's see, 4, 5, 6, 7. I'm going to go like this and just put an 8 there because I was not planning correctly. And so this is what I'm trying to find here. So I'm trying to find the net area from -2 to 8. Now notice what happens here. I'm going to go ahead and draw a line right there. I'm going to take out my blue and red. So this part right here is going to give me a positive area, and then this part of the triangle a positive area. This part of the triangle is a negative area, and then this right here is a negative area. So this is really what they want you to do. They want you to do this problem using geometry. Okay, the hard part first. If you have a circle of radius 2 and you're trying to find the area, okay, so the area of a circle is pi r squared. So if the radius is 2, the area is pi 2 squared, which is 4 pi. Okay, so that's the area of a circle with radius 2. Now we have a quarter of a circle with radius 2. So ours is not going to be pi. Ours is going to be a quarter of this. I mean, ours is not going to be 4 pi. It's going to be pi. So I said what it was going to be. So this one has the area of pi. Okay, let's go ahead and figure out what the area of this triangle is. The area of a triangle is 1/2 base, which is 2. Let's put a 2 right there. Times height, which is 2. So 1/2, 2 times 2. So this looks like it will give me 2 for the final answer. I mean, not the final answer to the integral. We haven't started doing the integrals. All we're doing is computing the areas. This one here is another triangle. Here's the base, here's the height. We're going to go 1/2 base times height, 1/2, 1 times 1, so this is 1/2. And then this guy right here is a rectangle that has the area of base times height. Now the height of this, if maybe we weren't very careful and paying attention, the height is actually 1. So you're going to go 1 times, and then what is that? There's between 8 and 3, and sorry about that, this is, we ran off the paper. It's going to be 5. Okay, so I think the hardest part of some of your homework problems is drawing the functions. And I picked one that was a little harder than your basic one on your homework. And then figuring out some areas. So now we want the net area. So the net area is going to be pi, because that's blue, plus 2, which is blue, and then we're going to go minus 1/2 minus 1/2, which is red, so that's why it's minus, and then -5. -5. So the net area is pi plus 2. Oh, what am I doing? Pi plus 7. No, it's not. Okay. Rewind. Okay, that is. Okay, what am I doing here? I'm going pi minus 3 minus 1/2. And so that's pi minus 3.5, but we're going to actually say pi minus 7/2. Okay. So there it is. That is the definite integral from -2 to 8 of the function. Most of the work was drawing the picture and looking at what those areas were. So pi minus 7/2. Now, this one won't be that hard because, I mean, most of the work is done. This is really asking for the total area, which then I would actually add all those numbers up. So this is going to be pi plus 2 plus 1/2 plus 5. So this is pi plus 7.5, which is really, what is 7.5? Okay. I think that's what I have here. 7.5. So that would be 15 over 2. And so I think that's what we're getting for the answer there. 5, 6, and this was 3 halves. Yeah, there it is. Okay, let's go ahead and do a few more problems just to kind of prep you for your homework. This one right here says if the definite integral from 0 to pi of sine x dx is 2, and in the next section or so we'll learn how to verify that on our own using calculus, using antiderivatives, then find the integral from pi to 0 of 5 sine dx. Okay, so we're going to go ahead and find it. So the first thing I'm going to do is I'm going to switch these so it says 0 to pi. Now, I can't just switch them without consequence. We can look at one of the properties. There should be a negative in front of that. Now I'm going to use another property where I am going to factor the 5 out, factor it out, and that's a way we can say it. We can put the 5 out front, so it looks like that. But I forgot the x there. Sine x dx. And then we know, this was the given right here. We see that right there. So this says -5 times a2, so the answer to this definite integral is -10. Let's go ahead and do our last problem. You get problems like this in your homework. So we have this right here. So we have the definite integral of a difference is the difference of the definite integrals. Now I'm going to write out more than some of you might want to write out, but that's all right. So I have that right there. Then we have minus the definite integral of 2gx dx. Then we have that other property that says we can factor out these constants out in front of the integral sign. So 10 times the integral 1 to 5 f of x dx. Factor out the 2, minus 2 integral 1 to 5 g of x dx. And look what we have. We're almost done here. We have this guy right here. Oh, wait a minute. And we have this guy right here. Okay, so here's the deal. You're going from 1 to 5 and computing the net area of this function. Well, we're given this right here where we're going from 1 to 3, and then we go from 3 to 5. And so, the wrong color. see if I can, oh yeah, perfect. So this is what I'm going to use for the brown part. So if my net area from 1 to 3 is 5, and then from 3 to 5 is 7 for the same function, then it just says I can add those together and get a 12. And that's what I'm going to do. 10 times 12. I'm going to do the same thing with these guys here, and I'll circle them in purple. So the integral from 1 to 3 of g is 6, and from 3 to 5, the integral is 8. And when I say integral, I'm saying, I'm thinking net area. So I'm going to add these two net areas, which is 14 when I add them. So it looks like I have 120 minus 28. So that's going to give me a 92. And so this completes 5.2. Do your homework and have a good day.